Okay, let's get started. Let's start our lecture. Okay, now lecture number 9. It will be devoted to linear differential equations, and we will continue to study the properties of the solutions. Okay. Linear differential equations of order n, and we will continue to study properties. Okay, first of all, I'd like to recall that we will consider a linear differential equation of the form so the function fn of x is multiplied by the derivative, the nth derivative of y, plus fn minus 1 of x times the n minus so the derivative of order n minus 1 plus plus f1 times y prime plus f0, let it be of x depending on x, f0 of x times y equals q of x. And we assume that the functions fn of x and so on, f0 of x and q of x are continuous on some interval I. I is an interval for the x, so x is between a and b. And we also assume that the first function fn of x doesn't vanish on this interval. Okay, so this defines the nth order linear differential equation. It is linear in y and its derivatives up to order n. And now we discuss the solutions of this linear differential equation, the existence of solution. Okay, and first of all, I'd like to formulate I'd like to state the following theorem. Theorem number 1. I will state it without proof because proof is too complicated. Okay. Okay, for the linear differential equation of order n, described above, described here, there is one and only one solution which satisfies the initial condition. So which satisfies the following initial conditions. We fix some point. So for any point x, for some point x0 from I, so we fix a point. And we are given the initial conditions. They look like so let's start with y. Y of x0 equals, let it be a0, y prime of x0 equals a1, and so on. And the derivative of order n minus 1 of x0 equals a n minus 1. Okay, given a point x0, so we take some point x0 in the interval, we fix this point, and we fix arbitrary constants a0, a1, and so on, a n minus 1. So we fix the constants, and under these conditions there exists a solution of this linear differential equation, and this solution is unique. Okay, so this is theorem number 1. It is the theorem on existence and uniqueness of a solution to the differential equation. Well, and now our goal is to construct, to construct solutions to the differential equation. And so we will need another theorem, theorem 2. Okay. Okay. We will consider the differential equation. So it is non-homogeneous differential equation due to some constant q, some function q of x in the right hand side. Right, we have a function q of x, but we can consider the complement differential equation. It is homogeneous differential equation, and so together with this differential equation we will consider an equation of the form of this form. So the beginning is the same, plus f1 of x times y prime plus just a moment, where is the the cloth. F0 of x times y equals 0. This is a homogeneous differential equation, and it is called the complement equation. So a homogeneous differential equation. And in order to solve a non-homogeneous differential equation, we should first solve the homogeneous equation. So we will discuss the problem on solving the equation, non-homogeneous equation, together with the complement, with this equation, with the homogeneous equation, which is a complement. So the complement to non-homogeneous one. Okay, I will use numbers. I think I will call the original equation number 1, and the corresponding homogeneous differential equation will be called equation number 2. Okay, so statement number 1 Okay. The differential equation 2, under these conditions, under these requirements, the differential equation number 2 has exactly n, so has n linearly independent, not exactly, but more correct, has n linearly independent solutions. Okay, that is solutions. I mean functions, that is functions y1 of x, y2 of x, and so on, yn of x. They are linearly independent. In the sense of the definition given in the preceding lecture. So on the preceding lecture, I have defined the notion, I have introduced the notion of linear dependence or independence of functions. So these functions are linearly independent. This means that there are no non-zero constants such that this linear combination vanishes for any x from the interval. So n linearly independent solutions. Well, statement number 2. This statement was proved during the previous lecture. So any solution of the homogeneous differential equation 2 can be represented as the linear combination of these n linearly independent solutions. I call it YC, and this subscript C means that this is a solution not to the original differential equation, but to the corresponding homogeneous differential equation. So YC is equal to, can be represented as the linear combination of these solutions. C with some coefficients, C1, C2 times y2 of x plus plus Cn times yn of x. So we can see that this is an n-parameter family of solutions. Okay. And statement number 3, it will be proved during today's lecture. So any solution of the original differential equation, non-homogeneous differential equation, can be represented as the sum of this general solution of a homogeneous differential equation, yc of x, and a particular solution of the original equation. So where yp of x is a particular solution of 1. Okay. So in order to solve the original differential equation, we can first find a particular solution or maybe guess a particular solution of this equation. So we need to know only one solution. And we must be able to solve the corresponding homogeneous equation. And if we find the n-parameter family of solutions, so all the solutions of the homogeneous differential equation, and after this we will add them together, we will find the general solution to the original differential equation, y of x. Okay, so part 2, well, part 1 is, so we will omit the proof of part 1. It is, I think, a little bit complicated. Next, part 2 was proved during the preceding lecture, and now we will move on to prove part number 3. So proof of part 3. Okay, so we need to prove two things. So first, let's consider two functions. So suppose yc of x is a solution of 2, and yp of x is a particular solution of 1. Then this means, so the first means that yc satisfies the homogeneous differential equation. So this means that fn times the nth derivative of y plus fn minus 1 times y to n minus 1 plus, and so on, plus n f1 y prime plus f0 y equals 0. It must be c, subscript c. So yc satisfies the homogeneous equation. Right, so we can write this. Next, yp is a particular solution of the original equation. And so we can write the following. Fn times yp, the nth derivative of yp, plus n minus 1 times yp, the derivative of 4n minus 1, plus f1 times y prime p, plus f0 yp equals 0. Next, if we add these two equations together, we will get the following. So add them and combine similar terms, right? We will get the following. Fn times yc plus yp, the nth derivative. So if we add these two terms together and use the linearity of the derivative, we can rewrite the sum in this form, right? This is the sum of these two first terms. Next, plus fn minus 1 times yc plus yp, the derivative of 4n minus 1, plus dot dot dot, plus f1 times yc plus yp prime plus f0 times yc plus yp equals 0. And this proves q of x. So just a moment, thank you. So I have mistaken. So it must be q of x, right? Because yp is a particular solution of the original equation, so it is equal to q of x. And so the sum must be q of x. So this means that the sum of these two solutions will satisfy the original equation, right? And so therefore, yc plus yp is a solution of 1. Okay, so the next, we must show that so we must show the following. Suppose we know n linearly independent solutions of equation 2, and we can find their linear combination, right? So all linear combinations with arbitrary constants. And suppose we know some particular solution yp to the original differential equation. Then I want to show that, so if y of x is a solution of 1, then it can be represented in the form yc plus yp, where yp is the given solution. So it is found in advance, right? So we know some particular solution, and our goal is to show that any solution of the original differential equation can be represented as this given equation, this given solution, this given particular solution plus this general solution of a homogeneous equation. Okay. So to show this, so I need space. Okay, I will use this part. To show this, suppose, so I want to show this, but y of x is a solution. Since y of x is a solution, then it satisfies the following equation. f1 times y prime plus f0 times y equals q of x. And we have, we're given y particular. So we know that this is also true for the particular solution. Q of x. Then if we subtract, we will get the following. Fn times y minus yp, the nth derivative, plus Fn minus 1 times y minus yp, the derivative of for the n minus 1, plus so on, plus Fn times y minus yp, yp, the derivative, plus f0 minus y minus yp equals 0. If we subtract q minus q, we will get 0. We can see that the function y minus yp is a solution to the homogeneous, corresponding homogeneous equation, because we get 0, right? Because on substituting y minus yp in the homogeneous equation, we will get 0. Is a solution to the equation 2. But we know that the n-parameter family of solutions of 2 has the form of linear combination of n linearly independent functions. So we know that y minus yp equals c1 y1 plus dot 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 plus cn yn. So this proves that y of x can be represented as yp of x plus c1 y1 plus dot 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 plus cn yn. So proved. Theorem is proved. And we will use this theorem in what follows. We will try to solve linear differential equations, non-homogeneous linear differential equations, using this property. Okay, so this is the first part of my lecture, and now I want to work with Wronskians, because the Wronskians are very important in our subject, because we need to have methods to how to check whether whether n functions are linearly dependent or independent, because it is very difficult to having the functions. It's the very complicated job to try to find non-zero coefficients such that this linear combination is equal to 0, or prove that these coefficients do not exist. It's a very hard job, and so Wronskians will help us, and I want to develop theory of Wronskians. Okay. So we will discuss theorems on Wronskians. I'd like to recall that given n functions, on some interval I, we can construct the determinant, we can compute the determinant. It depends on the functions and on the variable x. And this is the determinant formed by, so this will be the function depending on x, and it is formed by these functions and their derivatives. The second row is formed by the derivatives of these functions at this point, at the given point x, and the last row will be the derivative of order n minus 1. On the previous lecture, we have proved the following theorem. So I'd like to recall the theorem. We will use it in what follows. Theorem says that if functions are linearly dependent, linearly dependent on I, then the Wronskian is identical 0, so vanishes identically on I. So this means that if, but this is unfortunately is not a criterion for any arbitrary functions. There are examples when the Wronskian is identically 0, vanishes identically, but the functions are not linearly dependent, are linearly independent. There are some examples. They can be constructed, for example, if we consider some symmetric interval from -1 to 1, we can consider two functions, f1, which is equal to x cubed, and f2 of x, which is equal to the absolute value of x times x squared. So these two functions are not linearly independent. So let it be, so example. These functions are linearly independent. Why they are linearly independent? So how to prove this? Why are they linearly independent? Okay, suppose not. Suppose there are two non-zero constants such that c1 times x cubed plus c2 times the absolute value of x times x squared is identical to is zero, is a zero function. So this should be satisfied at any point of this interval. And for example, it should be satisfied for x equals 1. Let's substitute 1 into this equation. So we have c1 plus c2 equals 0. And it should be satisfied for x equals -1. If we substitute -1 here, we will get minus c1 plus c2 again equals 0. So this means that it follows that c1 equals c2 equals 0. So this equation is satisfied only for zero values of the constants. So this proves that these two functions are linearly independent. And what are the graphs of these functions? The graph of the first function is this. So this is the graph of f1. And the graph of f2 will look like this. So we can see that the graphs are different, and so we can't. So if two functions are linearly dependent, then they are proportional, and their graphs. It can be seen on the graph of these two functions. But these functions are linearly independent. But what about the Wronskian of these two functions? What about the Wronskian? Let's try to find the Wronskian of f1, f2, and x. It will be x cubed, the absolute value of x times x squared. And next, the derivatives. So the derivative of this function is 3x squared. Now the derivative of this function. What is the derivative of this function? Absolute value of x times x squared.
3x squared for x greater than 0 and minus.
Right. Right. So we can consider these two situations. So f2 prime. I will leave it in this way. So I should consider two cases. When x is greater than 0, then the Wronskian is equal to x cubed, then x cubed, 3x squared, and 3x squared. So the Wronskian is 0. So the determinant of this matrix is 0. Next, if x is less than 0, then the Wronskian is equal to x cubed, so minus x cubed. Oh no, just a moment, x cubed minus x cubed, right? Minus x cubed. Then 3x squared and minus 3x squared, and the determinant is again 0. But we should check the point x equals 0. What about x equals 0?
Not differential.
So can we differentiate this function at the point x equals 0? We can do it using the definition of the derivative. Let's find the derivative of this function f2 using the definition. So by definition, is equal to the limit as x approaches 0 of the function, the absolute value of x times x squared minus 0 divided by x. Right? Am I right? What about the definition of the derivative? The definition, so the definition of the derivative, I'd like to recall it then. So it is delta x approaches 0, or maybe h approaches 0. Which notation did we use?
Anything is fine.
Okay, right, f of x plus delta x minus f of x divided by delta x. Right? So I don't want delta x, right? Our initial point is 0, so it's this. Let's try to find the limit. It will be equal to the absolute value of x times x. If we divide by x, we will get this. Does it exist? Yeah, it is 0. So this function is differentiable at 0. Then the Wronskian of these two functions at the point 0 will be equal to 0, 0, 0, 0 is 0. So the Wronskian vanishes identically on this interval, but the functions are not linearly dependent. So this proves that, this explains that the converse is not true. If the, so given the functions, if we find the Wronskian and if it is identically 0, then this doesn't imply that the functions are linearly dependent. Okay, is it clear? So we have only this implication. If the functions are linearly dependent, then the Wronskian is 0. But we can use this statement in the reverse order. So using the logic, if the Wronskian is not 0 at some point, then the functions are linearly independent. So if A implies B, then it follows that the negation to B implies the negation of A, right? So, and using logic, we get this statement. But now, if we consider the functions, not arbitrary n functions, but the functions satisfying the homogeneous differential equation, we can get that so vanishing of Wronskian at a point is a necessary and sufficient condition, but not for arbitrary family of functions, but only for the functions that are solutions to the differential linear differential equation. Okay, well. Okay, now we will suppose that the functions f1 of I don't know, want to use f, y, let it be y, y1 of x, yn of x are solutions to the homogeneous differential equation of the form fn times nth derivative plus this and so on plus fn times y prime plus f0 times y equals 0. Okay. So we will prove. It will be theorem number 3. So we will start with the theorem. Okay. So if theorem number 3, if there exists a point x0 from the interval, from our interval I, this interval comes from the domain of this homogeneous differential equation. So all the functions are continuous on the interval I. So I comes from the differential equation. If there exists a point such that the Wronskian of these n functions is 0, then these functions are linearly dependent. Linearly dependent on I. So it is a sufficient condition for linear dependence on functions, of functions on I. Right? You may compare this theorem with a general case of functions. Even if the Wronskian vanishes identically on an interval, it may not imply that linear dependence on functions. But it implies linear dependence even if the Wronskian vanishes at just one point. Right? So we will prove it. We will prove this theorem. I think it's time. I think it's time to have a break, right? Let's continue our proof. So suppose there is a point such that the Wronskian is 0. So let's consider the Wronskian and substitute the point y1 of x0, yn of x0, y1 prime of x0, yn prime of x0, yn, the derivative of order n minus 1 of x0, it's y1, of x0 is equal to 0. Using linear algebra, theorem from linear algebra, if the determinant is 0, then if we want to solve the following linear system, let's consider the linear system of the system of linear equations. C1 times y1 of x0 plus and so on plus Cn times yn of x0 equals 0. And the second equation will be C1 times y1 prime of x0 plus dot 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 plus Cn times yn prime of x0 equals 0, and so on. C1 times y1 the n minus 1, the derivative of n minus 1, Cn times yn, the derivative, equals 0. What can we say about the solutions of this linear system of equations? So this is the linear system involving n variables. What are the variables of this equation? Do you know? What is your opinion? What are the variables of this linear system? So y1 of x0 and so on, yn of x0, and their derivatives are given. So we know that these functions are solutions. We are given these functions. We can compute these values. Okay, so C1 and so on, Cn are variables, right? So these are equations in the variables C1 and so on, Cn. So system, linear system, in the variables C1, C2, and so on, Cn. We want to solve them. We want to find the non-trivial solutions of this linear system. Is it possible or not? Are there any non-trivial solution of this linear system? So the number of equations is the same as the number of variables. So the criterion, so in linear algebra, from linear algebra, we know that the non-trivial solution exists if and only if the determinant is 0. But it is, right? We can see that we're given that the determinant is 0. So since is 0, there exists non-trivial solutions. The numbers C1 and so on, Cn, which are not all 0. They are not all 0. Okay, so let's consider the function y of x, which is equal to the linear combination of the given functions with the coefficients, with these coefficients that are solutions of this linear system. What can we say about this function? Is it true that it satisfies this homogeneous equation, differential equation? The first question, will it satisfy this equation? Yes, by theorem proved on the previous lecture. And today I have recalled the part. So this was the second part of theorem number 2 formulated in the beginning of the lecture. Right? So by part 2 of theorem 2, it is a solution. Okay, this is equation number 2 of 2. By part 2 of theorem 2. Right, it is a solution. So now let's speak about initial conditions. Which initial condition does this solution satisfy? do you know y of x 0? What is y of x 0? 0. Because of the first equation. Right? It is 0. What is y prime of x 0? Also 0, right? It comes from the second equation, the second condition, right? And the derivative of order n minus 1 of x 0 is 0. So this is a solution, and it satisfies these initial conditions. Okay. What do you know about the uniqueness of the function satisfying the solution of the homogeneous equation satisfying initial condition? Is it unique or not? So it is unique. By the same theorem 2, part 1, it is unique. So not part 1, it was maybe, right, it was, no, it was part 2, just a moment. So which part? So it was theorem number 1. By theorem 1. By theorem 1, the function satisfying these initial conditions is unique, right? Is unique. But I know the function, I know one function which satisfies 2 and satisfies these initial conditions. This function is constant, it is identical 0. I know that, so the first fact, the second fact, fact number 3, y of x, which is identical 0, so this function satisfies this. You can try, you can substitute this function into the equation and check that this trivial function satisfies this equation, right? It is easy. And this function satisfies these initial conditions. But we know that the function satisfying with these properties is unique. Unique by theorem number 1. And this means that this function is identical 0. Right? This means that y of x, which is equal to c1 times y1 of x, cn yn of x, is identical 0. Is identically 0. Equal, so is 0. Is a 0 function. Well, but this proves that the functions are linearly dependent. So by definition, next, by definition of linearly dependent function, y1 of x, yn of x are linearly dependent. Linearly dependent. So we start with the fact that the Wronskian vanishes at just one point. But this implies that these functions are linearly dependent. So the Wronskian vanishes at all points from the interval, of the interval. But this is true only if and only, so this is true only if these functions are solutions to the homogeneous differential equation. If the Wronskian vanishes at one point, then it vanishes at all the points and the functions are linearly dependent. So I can state this as a corollary. Let it be corollary. theorem is proved, and now the corollary. If y1 and so on 1n are solutions of the equation 2 on an interval I, then the Wronskian of the set of functions is either identically 0 on I, or it is not 0 for any x in I. So, or it is not 0 for any x in I. So this is a corollary of our theorem. Well, this is the part of theory which will be used later. But now we should consider, so go back to linear differential equations with constant coefficients. So our ultimate goal today, or maybe we will continue this during the next lecture. So our ultimate goal is to be able to solve the linear differential equation with constant coefficients. We have obtained some results on the previous lecture. I will recall these results and I will go a little bit further. We want to consider linear differential equations with constant coefficients. And let them be homogeneous. So we will consider the equations of the form the nth derivative plus an minus 1 times yn minus 1 plus a1 y prime plus a0 y equals 0. We will start with the homogeneous linear differential equation, and at the end of our today's lesson we will discuss non-homogeneous equations. So let's start with the equations with constant coefficients. On the preceding preceding lecture, so a week ago, we have discussed that so it is reasonable to look for solutions in the form e to the power lambda x, and we have derived from this assumption that this is a solution of our differential equation, let it be 3 of 3, if and only if it is a solution of the characteristic equation. Which can be formed from this differential equation in the following way. So lambda to n plus a n minus 1 times lambda to n minus 1 plus dot 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 plus a1 lambda plus a0 equals 0. So the way of solving the linear differential equation with constant coefficients, homogeneous differential equation, is the following. So first we should create the characteristic equation, solve it, find the roots of this characteristic equation, and we have considered the first case when all the roots are different and real. So suppose this polynomial has only simple roots and all these roots are real. So we have n real roots. They are different. And then we can form n linearly independent solutions e raised to lambda 1x and so on, e to lambda nx. They are linearly independent. This can be proved if we find the Wronskian. The Wronskian is equal to the van der Monde determinant. It is not 0, and so these functions are linearly independent, and so we can form the n-parameter family of solutions if we take the linear combination of these functions: c1 times e to the power lambda 1x plus c2 e to lambda 2x plus dot 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 plus cn e to lambda nx. So this is a solution. Now we need to consider the cases. The first case when so we should consider the case when this polynomial has multiple roots. Suppose it has multiple roots or repeated root. I will use the second order linear differential equation for simplicity, but the results will be generalized to the differential equation of an arbitrary order n. Okay, so we will consider the case when the polynomial has multiple roots. Real roots. Okay, for simplicity, let's consider a differential equation of order 2. And the characteristic equation lambda squared plus a1 lambda plus a2 equals 0. Okay. Suppose it has a multiple root. Suppose that discriminant, which is equal to a1 squared minus 4a2 is 0. So suppose that a1 squared minus 4a2 is 0, and lambda is a multiple root. So lambda is a multiple root. Well, then the function which is equal to e to the power lambda x is a solution. it can be easily proved by taking the first and the second derivatives and substituting into the original equation. So this is a solution. But what can we do with the second solution? Okay. It seems that we have, since it is a multiple root, is a root of so there are two repeated roots, right? Lambda is a repeated root, right? So we can form two functions. y1, right, y1 is this and y2 is the same function as before. If we proceed as before, we can form these two functions. But it is not true that a general solution is equal to the linear combination plus c2 e to lambda x. Because actually it is not two constant, it's just one constant. So we need the second function to satisfy this equation. How to find the second function, do you know?
If it repeats one time, x e to the power lambda
X times this, right? But maybe let's derive this fact. Let's start with the following. We will look for the second solution represented in the form, let it be some function u, so y of x equals u of x times e to the power lambda x. And we want to find the function u of x. Let's try to find the function. Let's substitute this into our original equation. So we need to find y prime. It will be equal to u prime. So it is equal to e to lambda x times lambda u plus u prime. y2 primes is equal to e to lambda x times lambda squared u plus 2 lambda u squared plus u2 primes. So not squared. What's this? Well, let's substitute into the original equation. We will get lambda squared u plus 2 lambda u prime plus u2 primes. It is y2 primes, so plus a1 multiplied by this and plus a2 multiplied by the original function, so u will be u. It must be equal to 0. We can divide by e to the power lambda x. And we have the following: u2 primes plus 2 lambda plus a1 u prime. We combine this, and plus lambda squared plus a1 lambda plus a2 times u should be equal to 0. But since lambda is the root of this polynomial, of this characteristic polynomial, it follows that this is equal to 0. This coefficient is 0. What about the second coefficient? So we know that lambda is a multiple root. Lambda is a multiple root. Since lambda is a multiple root, I will write it here. Okay, so this means, or maybe do you know that if lambda is a multiple root of a polynomial, then it is a root of its derivative. The root of its derivative. Or maybe we may use the following. Do you know the, just a moment, divide theorem? So what is the sum of the roots? Lambda 1 plus lambda 2 is equal to negative minus a1, right? So, but if we have the multiple root, then we have the following: 2 lambda equals minus a1. So you can see it here, right? So 2 lambda plus a1 is also equal to 0 due to the fact that lambda is a multiple root. Then we are left with the equation u2 primes equals 0. So if we are looking for the solution represented in the form of the product of some function u with e to the power e to lambda x, then you must satisfy this equation. But this means that u is a linear function, as Cassie told. Right. So this means that, so since u2 primes equals 0, this means that u of x can be represented as c1 plus c2x. Using the reasoning, if we start from the end of this reasoning and go to the beginning, we can prove that any function of this form will satisfy our differential equation. So the solution, the general solution, will be given by the formula y of x equals c1 plus c2x times e to the lambda x. So this is the case of the differential equation of order 2. But if we have a differential equation of an arbitrary order, and if we have a root which has the with the multiplicity k, for the root of multiplicity k, we should write the following linear combination: c1 plus c2x plus and so on plus c. So it must be ck times x to the power k minus 1 times e to lambda x. If lambda is a root of order k, then the solution is represented in this form. And if, for example, we have let's consider something like let it be the differential equation of order 6, a5 y a0 y equals 0. And suppose our characteristic polynomial has the form. Let it be lambda minus maybe lambda 1 to the power 3 times lambda minus lambda 2 to the power to the second power and times lambda minus lambda 3. So lambda 1 is the root of multiplicity 3, this is the root of multiplicity 2, and this is the simple root. Then the solution, the general solution, can be represented in the form. So for the multiplicity 3, it will be c1 plus c2x plus c3x squared times e to the power lambda 1x plus c4 plus c5x times e to the power lambda 2x and plus c6 times e to the power lambda 3x. So for each root with some multiplicity, we should write this part, this function. Okay. And maybe, so what shall we do? So now start the lecture. So, right, we should finish the lecture, and next on the seminar we will continue to discuss this. So we must discuss the case of the complex roots, and we will try to solve the examples.